Attention is all you need. Part 2. Background. What came before. In Part 1, the authors identified the problem, sequential computation, the bottleneck that makes RNNs slow and hard to scale to long sequences. But they weren't the first to notice it. Other researchers did too and tried to work around it. Part 2 is where the authors take us through the graveyard of near misses, the approaches that moved the field forward but didn't fully break the bottleneck. They show what came before, why each solution had a catch, and how that sets up the transformer as the first model to commit to attention all the way down. Once you see these alternatives, you'll understand why the transformer's bet was such a radical departure. Let's take them one by one. Alternative 1. Convolutional neural networks. Some researchers had the same goal, reducing the need to process information one step at a time. Their solution? Use convolutional neural networks instead of recurrent neural networks. The main models here were Extended Neural GPU, ByteNet, and ConvS2S, which means convolutional sequence to sequence. Here's their thinking. CNNs are great at parallel computation. They can compute calculations for all positions simultaneously, not one at a time like RNNs. Problem solved, right? Not quite. The problem wasn't solved, it was just shifted. The issue was how these models connect information from distant positions. Let's say you're translating a sentence, and the first word needs to inform the translation of the last word. How many computational steps does that take? With ConvS2S, the number of steps needed to connect two positions grows linearly with the distance between them. With ByteNet, it grows logarithmically. Better, but it still grows as distance increases. With the transformer, it's constant. Positions can connect directly in a single step of self-attention, no matter how far apart they are. Why does this matter? Because every extra operation dilutes the learning signal. It's like the telephone game. The more steps information has to pass through, the more it degrades. This makes it harder for the model to learn long-range dependencies between distant words. Now, the transformer does have a trade-off. All that averaging of attention-weighted positions can reduce fine detail. But the authors mention they counteract this with something called multi-head attention, which we'll get to later. Alternative 2. Self-attention as a supporting actor. Self-attention, sometimes called intra-attention, is when a model looks at different parts of a sentence to understand each word better. It's basically the model asking, which other words in this sentence matter most for understanding this particular word? In parts 0 and 1, we mentioned that self-attention already existed before the transformer, and it had already proven successful in several areas: reading comprehension, text summarization, determining if two sentences mean the same thing, and creating general sentence representations. So, self-attention wasn't the breakthrough invention. The breakthrough was making it the star of the show. Up to this point, self-attention was always a supporting player, a useful component tucked inside larger, more complex systems. It had never been the foundation of a complete translation model. The transformer changed that. It said, what if self-attention didn't just help with translation? What if it was the translation system? Alternative 3. End-to-end memory networks. The paper also mentions end-to-end memory networks. These took a different approach from classic RNNs. Instead of processing sequences step by step, they used a repeating attention mechanism that kept looking back at stored information. Think of it like having a conversation where you keep referring back to your notes, rather than trying to remember everything in order. These networks showed promise on simpler tasks, answering questions about basic texts and predicting the next word in sentences. But they had limitations. They weren't designed as complete translation systems that could handle the full complexity of converting one language to another. They were more like specialized tools rather than general-purpose translation engines. The Transformer's unique position. The author's claim is bold. To the best of their knowledge, the Transformer is the first transduction model that relies entirely on self-attention. No RNNs processing sequences step by step. No convolutional layers. Just attention. That's the revolutionary bet. Attention isn't a helper anymore. It's the entire architecture. For the first time, a model could relate all parts of a sentence directly, decide what matters, and translate effectively, without sequence-aligned recurrence, forcing it through a token-by-token chain. No convolutions, just pure attention doing all the heavy lifting. So now you've seen the alternatives, the progress, and why none of them fully broke the bottleneck. In Part 3, we finally meet the Transformer itself. We'll start with the big-picture blueprint before we dive into the details.